We'll start with the first main group family, group 1A, which features the alkaline metals. Now on the periodic table, it starts with having your lithium, your sodium, your potassium, your rubidium, your cesium, and your francium. And they are located in that first column on the periodic table. They tend to be highly reactive and they're highly alkaline. And because of this high reactivity, you never find them naturally in nature. So whenever we hear potassium, like the potassium in bananas is actually the ionic form. Looking at group 2A, main group elements, these are the alkaline earth metals. They include beryllium, magnesium, calcium, strontium, barium, and radium. And they are lustrous metals, and they have less reactivity than group 1A, but they're still not found in their pure state in nature. Now skipping over to group 7A, that features the halogens. It has fluorine, chlorine, bromine, iodine, and acetine. They're colorful and corrosive. They're found in nature only in combinations with other elements like sodium chloride or table salt. And the group name halogen is actually taken from the Greek word halos, which means salt. Group 8A are the noble gases. They entail helium, neon, argon, krypton, xenon, and radon, and they get their title from just being less reactive, and they don't react with other, or you generally don't react with other chemicals. There are some notable exceptions, but they're far and few between. The helium, neon, and argon, they don't combine at all, whereas you might have some reactivity experience with krypton and xenon when combined with some things. Now, in terms of identifying these elements, there's a specific way of aligning them and distributing their electrons. And so each atom has a characteristic number of electrons, but that grouping or how they're delegated or emanated from the actual core of the nucleus of the atom has a kind of specific ordering. And so we'll be talking about that next. Now, the farther a shell is from the nucleus, which is where the electrons are going to be placed into, the larger it is. And so the more electrons it can hold, and then higher energies that are required to keep those electrons intact. Now the first shell, which is closest to the nucleus, can hold 2 electrons. The second can hold 8, and the third can actually hold 32. Now within these shells are these things called subshells. And the subshells are important, and they're going to be important going forward, and they have 4 different types. They are identified as S, P, D, and F in order of increasing energy. Now the first shell has only an S subshell. The second shell has an S and a P subshell. The third shell has an SP and a D subshell. And the fourth has SPD and an F subshells. Now as we go forward, you're going to want to make sure you familiarize yourselves with the S, the P, D, and the F, because they're very going to be uniquely important when we start getting into electron configuration and the alignment of those electrons with respect to the atoms. Now, the number of subshells is actually equal to the shell number. And the specific subshell is symbolized by writing the number of the shell followed by the letter for the subshell. So within each subshell, the electrons are grouped into orbitals, the regions of space within an atom where the specific electrons are most likely to be found. And so this is their way of predicting where electrons are going to be located on a respective atom. Now an S subshell has only 1 orbital. A P subshell has 3 orbitals. Each orbital can maintain at most 2 electrons. So as we're talking about this, keep in mind that while S has 1 orbital, it can maintain 2 electrons. P, while it has 3 orbitals, it can maintain 6 electrons at most. D, while it has 5 orbitals, it can maintain a grand total of 10 electrons for the entire D subshell. And for F, it has 7 orbitals, which can maintain a total of 14 total electrons for the F subshell. Now, each orbital individually does fit 2 electrons, each spinning in a different direction. Because remember, electrons tend to repel each other. And so when we're talking about orbitals, we're basically using that to kind of get a picture of where those electrons are going to be placed geographically with respect to the atom. Now, different orbitals have different shapes and different orientations. Orbitals, for instance, in the subshells have more of a spherical shape to them, whereas P subshells are roughly something called dumbbell shape. But a lot of times when I've drawn it, it looks kind of like the pin of a bowling ball pin in terms of occupancy of space. Now, as I mentioned, the orbital can hold a maximum of 2 electrons, each exhibiting opposite spin. The first shell has one s orbital and holds at most 2 electrons. The second shell holds 8 electrons, 2 in the 2s orbital and 6 in the 2p orbitals. The third shell holds 18 electrons, 2 in the 3s orbital, 6 in the 3p orbitals, and 10 in the 5 3d orbitals. The fourth shell holds 32 electrons, 2 in the 4s, 6 in the 3 4p orbitals, 10 in the 5 4d orbitals, 14 in the 7 4f orbitals. And so in terms of the overall distribution of electrons, this is how they break down. You have your shell being 1. In 1 you're going to have the s. In your second shell you'll have the s and the p. In your third you'll have s, p, and d. And in the fourth you'll have s, p, d, and f. And these all go with or align with the electron capacity. Now, when we start talking about the arrangement of these electrons, it should make for a better picture in terms of understanding this arrangement of these shells that I've already mentioned. So, when it comes down to the electrons, each atom has a certain number of electrons, and those electrons are distributed based on those energy levels. And so those energy levels are kind of broken down starting at 1s, and it goes up with the increase in the subshell number. So long story short, electrons that are going to be found in the 5p subshells are going to be higher energy than the ones in the 1s. And they fill up these energy levels one by one, electron by electron. Now this depiction here, while it's probably better when it's drawn out on paper, this gives you a general order of how the energy levels flow. You have your 1s, and then after 1s, it goes your 2s, and then after your 2s, from there you go to your 3s, and then, not 3s, you go to your 1s, your 2s, and then you have your 2p and 3s, and they increase from there in terms of order. Now 1s represents the lowest energy, and as you go up, 7p represents probably a higher energy. Now, as you're going through this process of these energy levels, they're filling up with electrons, and the electrons are distributed in that fashion. Now here is an example of how that's written in shorthand, where they take that order represented before and you fill it by the exponent number that fits inside of it. Meaning, if you look at the order we talked about, you have your 1s being the first energy level. At most, that 1s can fit no more than 2 electrons. Likewise, if you look at your 2s, it can fit no more than 2 electrons. If you look at 2p, it can fit no more than 6. And the order is just like I mentioned, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, so on and so on. And you fill the electrons up accordingly. Now, each one has a maximum amount of electrons that can fit in that subshell. As I mentioned, 2 can fit at most, S can fit at most 2, P can fit at most 6. Now the D that I mentioned earlier can fit at most 10 electrons, and then F fits at most 14 in its total subshell. And then and this chart is just kind of a general breakdown of those electron configurations and how those electrons are dispersed based on the atom in question. Here hydrogen would be written 1s1, helium goes 2, 1s2. Here you have lithium where it has 3 electrons and it goes 1s, 2s, so on and so on. And you could actually keep going up if you were looking to increase the total number of electrons to represent another atom. Now, Electron configurations are used to kind of describe the number and subshell letter in order of increasing energy, and the graphical representation is very helpful in understanding how certain chemistries actually happen. There is also a notable shorthand expression of electron configurations that is used where they reference the noble gases as kind of a starting point. So in this slide here, we're showing the various ways that boron can be expressed using electron configuration. You have boron, and this is one way. This is your standard form of writing electron configuration. This is your diagram form of electron configuration, and this is the abbreviated form of electron configuration. Now, if you have a periodic table in front of you, what happens is you use the noble gases as kind of a reference point, and it saves the space for those electrons, so to speak, that ordinarily you would write. And this would come in handy for elements that are larger in electron number. So here we have another group of elements. Notice you have your oxygen, you have your fluorine, and they're going in order based on the electron configuration order, and they increase. Now, if you look at the periodic table, they're actually broken up into blocks where you can almost identify where an element would be found, or in terms of its highest energy level. There's the X block, which is found in the main group element columns of 1 and 2. You have your P block, which generally is found in that region of your transition metals and intertransition metals. You have your D block, which is going to be found in the bottom extremities of the periodic table. And the P, let me go ahead and add to that. Sorry, let me back up. The D block is going to be found where your transition metals are. Your P block is going to be found on the right side of your periodic table. And then your F is going to be found in the bottom of the periodic table below the transition metals in the lanthanide and actinide series. And here's that image for clarity's sake. Once again, your S's, any element's going to be found. The highest energy level for those elements are going to be in these respective regions. So the highest energy for that would be S. Then if you go to your transition metals, you notice this D here. And then here you have your P's, any of the elements that's in the P. And then down here you have your F's to kind of go along with those. Now, for clarity purposes, for chemistry, main group elements, there's a popular vocabulary called the valence electrons, and they apply to other electrons, but especially when you talk about the main group electrons, because they describe a plethora of reaction chemistries. But valence refers to available electrons, or outermost, as they're referenced when talking about electrons. And the groupings of elements, the main group ones, have a specific valence assigned to each one. And so if you have your periodic table, it helps to know that maybe the column 1 main group is +1, meaning they have 1 valence electrons. The column featuring beryllium has +2, so everything in that is going to have 2 valence electrons. And then you skip the valley all the way to the part of the periodic table where it features boron, and it has 3 valence electrons, and then you go on all the way until you reach 8A. And so those are important because they dictate what type of reaction chemistries elements will be willing to engage in. And so these are just some of the listings of those. You have your lithium, sodium, potassium, rubidium, cesium. They are in group 1A. They generally have 1 valence electrons that is readily available for reaction. You look at 2A, they have 2. You look at 7A, they have 7, and they don't lose those 7 for reaction chemistries. They generally are willing to kind of accept some, and so their valence number is 7 for total number of electrons in their outermost shell. But when we learn about their reaction chemistries, we'll see how they actually interact with some of the group 1A and 2A elements. And we have our group 8A, which those are generally going to be your more stable elements that don't engage in reaction chemistry. And then lastly, we want to talk about electron dot symbol notation. And if you know your valence electrons, you can essentially attach a dot notation for each element. Notice column 1A has one dot, column 2A, where you have beryllium, has two dots, 3A has three dots, 4 has four dots, nitrogen, 5, oxygen, you have your 6, and then you have your 7 here with fluorine. And then for your noble gas conformation, you have 8 dots. And that is used to kind of denote the amount of valence electrons that are available for chemistry.